do hundreds of nanometers, right? So that's why on this talk, mostly I'm going to talk about electron microscope to study nanoscale features. So electron microscope, there are two types of electron microscopes. I don't know whether everybody is familiar with this. Everybody knows, right? So something called the transmission electron microscope. That means your electrons are, this is your sample. So electron beam is passing through the sample. Or you can have electron beam coming here, you can scan the electron beam, then look at what is coming out. So that is called the SEM, scanning electron microscope. So I'll talk about these two. In the transmission electron microscope, you can look at even features in the angstroms, even atomic scale. You can see atoms, right? Yeah, not as good as STM that I'm going to talk about, but you can look at angstrom scale features using TEM. But scanning electron microscope, they are good to study surface properties, right? So, but they can only do something from maybe few nanometers. So I'm talking about maybe greater than 1 nanometer. You can see if you have good scanning electron microscope. So this is some details. I don't think I have to go through that. So if you this some of typical transmission electron microscope. Do you have one here in this campus?
We have one in the
materials.
No. It looks like this.
Oh really? Okay. Basically what you have is the electron source, the sample, then everything is about lenses, right? To focus, but here lenses are not optical lenses. They are either capacitors, electric fields and magnetic fields, right? You have magnets and some parallel plates to focus. So then basically you can create the image here. So you can either view from here or you can project onto a screen. So using a CCD camera. So this some of the features you can see from transmission electron microscope. They are not high resolution, but there are very high resolution TEM. That's we have in our campus. You have done that one. With that one, you can do even atoms like that. You can see this is some crystalline material. These are individual atoms. You can see this is some amorphous material. So you don't see that crystalline structure. Right? So if you have a high resolution TEM, you can look at the atomic configuration. If you have some missing atom or something, that also you can see from this transmission electron.
We can see vacancies and dislocation.
Oh yeah, you can see some dislocation bands. Yeah. So also later I'm going to talk about, everybody familiar with the diffraction. So this is, we are talking about electron diffraction. If we have electrons coming, if it gets diffracted. So you can look at your K1, K2. If you have this K2 minus K1, if this is some close to what is called the reciprocal wave vector. So you can see the diffraction pattern. So that's, you can see some diffraction pattern coming from this nice crystalline structure. That's why you have a regular diffraction curves here. Here, since they are amorphous, no crystalline planes, right? That's why you get this kind of rings here.
No long order.
No, exactly. This one, doesn't have short range order. For the diffraction, you need to have the short range order. So this one may have some long range order, but that's not enough to give these spots. But you can get rings like that.
Some of our guys have experience in the calculation of
Oh yeah. We always do.
in small order.
Right, yeah. So, but how to index these things, so that's different. So, scanning electron microscope, like I said, they are good to look at features greater than 1 nanometer. Mostly you can see how good is your surface, whether it's corrugated surface or flat surface, things like that you can easily see from scanning electron microscope. So first, when you talk about these microscopes, these are all electrons, right? First you need to generate electrons. How do you generate electrons? There are two techniques they use. One is called the thermionic emission. So you just heat a filament, then you can emit electrons, right? That's called the thermionic emission. So, long time ago, most of the electron microscope used the field emission. Field emission is you have to apply very large voltage, like kilovolts, then you can emit electrons from. So, if you have first one, use this. Yeah. If you heat something, right, apply very large one, very high temperature, it will emit electrons. That's one way to do it. So other one is if you have very high, like maybe 100 kilo electron or so. Yeah, kilovolts, 10 kilo. So then you can emit electrons between these two, right? So that's called the field emission. So here you talk about the thermionic emission. You have to have enough energy to go over the barrier. In field emission, they can tunnel through the barrier here.
Tunnel?
Yes, it's because this is the suppose your electron. This is the barrier, right? So if you have electron coming with some energy, it cannot go through unless you can make this barrier small, right? By applying very large voltage, you can make this barrier like this. Then these high energy electrons can go through. That's the field emission.
Yeah.
Thermionic emission means you have to have enough energy to go over the barrier. So that is this one.
Тут понятно все?
Thermionic is, see, you have to go over the barrier too. Sorry. So you can see this barrier is called the work function, right? So I don't know if you're familiar with that term. Work function is an energy given by electron volts. So for metals, this work function is very big.
Работа выхода.
So they are like 5 electron volts. That's very big. So that means you need temperatures like about 2000 Celsius to emit electrons. But if you can make this one smaller, that means you can easily go over this one, right? So things like cesium, they have work function about much smaller, like 1 to 2. So that means you can emit electrons at lower temperatures. Even this lanthanum as hexaboride, they have about 2.6. Others are all very large numbers, right? So thorium, another one. Thorium also has very low work function. That's what they use in most of these electrons. So this is how to generate electrons, right? So what you need is, once you have the electron, so here you generate the electron. Now you have to pass the electron here you have to focus the electron, right? For that you need to have some magnets and some electric fields. So then you can focus it to the sample here. Now in the SEM, this electron beam is scanning. So then you can take this scattered light using a detector, you can generate the image. But this shows all the component here picture. So important thing is this scanning. So your sample is, the beam is scanning through the, you can do either beam or the sample also.
We do magnetic scanning using magnetic lens. Yes?
Oh yes, that's what we do, yes.
No mechanical movement.
No, yes, exactly, yeah. So in the transmission TEM, this is more like the optical microscope. So you have a light, you have an object, then you focus your light. So it's more like, here you have first electrons coming here, then you have your so then you can view from the other end. Optical microscope also you have to do same thing, right? You have source, then you have your objective, then you have eyepiece. So it's very similar to this one. You can see this is like the eyepiece to view this one. Then you have you illuminate means you expose to electron in this case. So then you have sample here. So it's very similar to optical microscope, except we use electrons instead of light. So, but TEM is very important. We can do two modes. We can do image mode, or sometimes we need the diffraction mode to get the diffraction pattern. It's very easy. Only thing you have to do is change these two apertures here. If you have this aperture on, you can mostly get the diffraction pattern on the screen. If you have this one out, this one in, you can start imaging the microscope. It's very simple. What we do is, first you take the picture. So after that, we just change the aperture and look at the diffraction pattern. So basically, you have
depends from aperture change results?
Yes, that changes your focal length and everything. So then you have to be in the diffraction mode. You need to get light diffracted from here, right? After this one. But here you just need to focus the image onto this one. That's the only. It's very simple. Only thing, just push and pull. That's all. Only two. Always we do the two. First you get the image, then immediately we change the one. So you can see here, just like in the optical microscope, your sample is sitting here, right? So then you, in optical microscope, you do the same thing. You have light, then through the sample, then you with the you have objective, then you have the eyepiece, just like that. So, sample, electron beam coming here, then you focus here. So depending on what you need, you can do diffraction or imaging. So then there's another, once you do, you can do the imaging first, right? You can look at all the features of the sample, then you do your diffraction, then you know what is the crystal structure. So then we can start the other things called this electron energy loss spectroscopy. This is also you can do in the same TEM. Only thing you need to have a ES detector. That's all.
It's special detector.
Yes, for the ES. Yes.
For the energy.
Yes. Yeah. So this means energy, electron energy loss spectroscopy. That means if you have electron coming here, so when it passes through the specimen, so it interacts with atoms, right? So then we know sample has a lot of vibrational modes, it can have some plasmons and some other transitions. So then if you have any event here, so that will absorb some of this electron energy, then whatever coming out is more like the inelastic scattered light, right? So if you look at that energy, that will give you some information about what is lost here. So then that you can see what is that due to either some plasmonic. So if you look at the yield spectrum, initially you are going to see big peak because there's something coming without any loss. So then you are going to see something called the plasmons, because if you have any metal, we know these atoms, they have these free electrons, right? These electrons are always oscillating, something called the plasmon. So you can have bulk plasmon or surface plasmon. So this, they can interact with those plasmon, then you get this plasmon peak. So then it becomes very small, then very small features, but these features, if you enlarge, you see a lot of this information. So this is usually spectrum that look like this, coming like this is the zero loss. So then you have the plasmons, then it comes like this, but this part, if you blow out, this will show a lot of these features. So these features are mostly coming, I think everybody is familiar with if you have atom, so we have this K, L, M, all these levels, right? So this we call the core electrons. So then we have the valence band, right? So these coming mostly because we have these electrons coming. Those electrons will remove some of these atoms, right? Whether it removes this one or it removes this one. Those are the features you are coming from these things. So because each atom has specific energy for these ones, right? If you take gold has, we know what is this energy for this one. If you take copper has different numbers. From that you can easily tell what kind of features you are getting here. So this is zero loss, then you have plasmon, then you have these co-electrons coming from that. So let me show you some. Okay, so that's one thing. So first we did the image, right? We just look at then we did the diffraction. So then we did yields. Then we can do something called the EDAX. This one is called energy dispersive X-ray analysis. So this you can easily tell what kind of elements are there. Suppose if you make some, say, carbon structure, sometimes you may have some impurity, right? If it is maybe some boron or oxygen or phosphorus, so we can look at those things using this EDAX. Sometimes they call EDAX, so sometimes they call here they call EDAX, so sometimes EDAS, different names. This is energy dispersed spectroscopy. So this is actually X-ray with this one. So what happens is, so when you still we are using the electron beam, right? Electron microscope still we are talking about. Your sample you are hitting with electrons. When you hit with electrons, some of these electrons can be removed, right? So suppose if you remove this electron, what happens? So some electron will come from here to here, right? So when this happens, you have some energy. That's X-ray. So then in E-dax you are looking at the X-ray spectrum. So from that we know that corresponding energy. From that you can easily tell whether this is like aluminum or gallium or titanium, nickel. So every element you can easily see from this one. This is very easy technique. So this called the, sometimes we call the elemental mapping technique. Element mapping. So you can map your material, what is there. So, but only thing you cannot see like hydrogen, lithium, those elements you cannot see. Yeah, these are too light. Yeah. But anything more than boron you can see from this one.
Ребят, ядерку вспоминаете, да? Как-то там все с уровня на уровень переизучалось, атомную физику, и то, что вылетает, будет соответствовать, будет иметь строго определенную энергию, и мы сможем определить, какой это элемент. Гамини, how works this sensor? How can we measure?
We have X-ray sensor inside the.
And how it works? We don't know.
Okay, X-ray sensors are more like it's a scintillator. So it's then they have some photomultiplier tubes. So that's more like radiation detector. Standard. Then we have something called the energy dispersive. Yes. That's, I don't know. People are familiar with the energy dispersion spectroscopy. So energy dispersion is basically you have this two energy, we call the discriminator. So you have the energy high, energy low. If you have some energy higher than this one and less than this one, we don't count it. If electron that's higher than this one, we count as 1. So if it is like this, we don't count. So then here also I think if it is less than that, we count as something lower than that one. So that's how the energy dispersive spectroscope works. Then this is fed to something called the scalar. So from that you.
And you need to have many levels for.
No. So only you have to have defined two energies. So between those two energies you have to, because these all come in the same energy range.
And what about resolution?
Resolution, I think this is really good. So I think they have, I cannot name the exact numbers. So except for that hydrogen and lithium, so I think the resolution is really amazing. You can identify boron, beryllium, any of those elements very easily. So also this one also important. This pulse height. That also you need to know. That will tell you the intensity of this, whether it is this one or this one.
Ребята, понятно, про что мой вопрос? Интересно, как именно мы измеряем энергию того кванта рентгеновского, который вылетел. То есть, как-то вот можно его зафиксировать, что он есть или нет, но мы же должны энергию померить, туда по оси X положить. Ну, видимо, тут деталей пока.
Я так понимаю, что каждому атому соответствует, каждому элементу соответствует свой уровень энергии. И вот он показывает, что сколько, вот, например, этой энергии выше нее вот этих чисел он насчитал на счетчике, и он показывает вот эту интенсивность.
А как он считает, выше или ниже, это же надо. Ну, окей.
Yeah, so this is I can do one lecture on the energy dispersive technique. I need to prepare some talks for next year also. Maybe that's those other things we can think about. Yeah. So also this E-dax you can do not just with the electrons. So you can even do with incoming X-rays also, because you can not these electrons. But since we are using the electron microscope, we can use that energy directly. So also there are some other spectra. This is very important thing actually is to understand. If you have an incident electron beam, there are so many things can happen, right? So if you have some called this brain problem. So this is the broad X-ray background. Okay. So then, if you have X-ray, we have this sharp peak, right? This is like copper alpha or copper beta kind of thing. So this is also coming from this scattering happening. So then this is where the X-ray is coming here. Then you can have sometimes some fluorescence like visible light coming. Then you have backscattered light. Then it transmitted. This is the zero loss electrons, right? So then you have the elastically scattered or inelastically scattered. Then also you can produce heat. Right? That's a phonon, right? So then you have OJ electrons. So that's another thing. I don't know if people familiar with OJ.
АЖ, да?
Yeah. So it's a secondary electron,
For
right?
light elements.
Yes, yeah.
Ребят, смотрите, Гамини говорит, что очень много всего происходит, когда электронный луч падает на образец. Начинают высвечиваться и рентгеновские лучи, и обратные электроны, и проходящие электроны, тепло начинает выделяться, вторичные уже электроны.
And this is, I'm going to talk about these two now. This something called XPS and also UPS. So I'm not going to talk about these two. This is using ions, not electrons. You have to use charged ions for the SIMS. This is very expensive instrument, SIMS and this time of flight SIMS. So I talk about this one now, XPS. This is mostly used for the surface characterization. XPS is basically you use X-ray light. So now nothing about electron microscopy. That now is a new thing. So we are done with the electron microscopy now. So now we are going to talk about the surface characterization. So when we actually yields also has some surface properties that I'll talk about later. Now talking about the surface. So to do this one we use X-ray to shine on the sample. So when you shine on the sample, then again you are going to knock out some electrons, co-electrons, right? So in XPS, we are directly looking at the energy of this outcoming electron. So we have detector. This is my detector. The detector will look at the kinetic energy of this outcoming electron. So it's not the one transition or anything. Directly when you knock out the electron, so when that electron has a kinetic energy, right? So we can measure that kinetic energy directly from the this detector. So XPS is again very ultra high vacuum chamber. So that has it's more like a big chamber with the ultra high vacuum. You have sample is here. Then we have X-ray source. So this is my say X-ray source coming here. So this is. So then we have detector here. So then this will directly measure the outcoming electrokinetic energy. So from there you can look at a lot of information. That's again what happens. Here we can look at if you this density of state. Everybody familiar with the density of state? So this basically your number of states per unit energy, right? Density of state. So at density of state as a function of energy, we know these are the co-electrons, K, L also has like 3 levels, right? M and all these things. Then you get to the valence band, right? So basically, this is your co-electrons, then this is your valence band. So then we have valence electrons. Everybody is familiar. So if you look at valence band, we have this occupied states up to the Fermi energy, right? I don't know if the people know. I mean, if you take valence band, you have states filled up to something called Fermi energy.
Fermi energy.
This is called the
Energy Fermi.
So then you have unoccupied states here, right? So if you want, you can promote electrons here, but this is the highest field state Fermi energy. That's what drawn here. You can see this is the co-electrons, this is the valence band up to Fermi energy here. Then we have something called a vacuum level. Right? So if I want to remove the electron from the surface, I have to provide that electron to come out, right? That's the work function here.
Это работа выхода, выкинуть его в вакуум, удалить из атома на бесконечное расстояние.
Vacuum means it's coming out of the your material, right? So now in the XPS you are going to shine X-ray. So then it will remove electron here. So this electron is what I am going to measure using this detector. I am directly measuring this kinetic energy of this electron. Right? So, but why we know that kinetic energy is what? So we have energy of the incoming photon, that's the X-ray photon. So then it has a binding energy, right? The electron has a binding energy. It has to overcome that binding energy. Then rest is the kinetic energy. You can write your kinetic energies, this one minus your binding energy, and also you have to, if it is coming out, you have to overcome the work function. You can easily say your h nu is basically total h nu, that is the incoming X-ray. This should be equal to, first you need to overcome the binding energy, right? Binding energy will make it detach from the atom. So then it has to come to the, because it has to come to the detector. So for that it has to overcome the work function. This is the work function. So then it is coming with some energy. That's a kinetic energy. So that means kinetic energy is h nu minus binding energy minus pi. Is that it?
Это фотоэффект обычный, да, который мы знаем, только еще тут энергия связи, кроме работы выхода, еще есть энергия связи, чтобы изотопно выкинуть. Правильно? Стандартно вот то, что мы написал.
So that means when you measure your, this is what you are measuring, right? So from that you can get information about, we know this one, we know the energy of the incoming light. So then we know the work function of that material. Then you can easily see what is the binding energy. So each element has specific binding energy. From that you can easily identify what materials are already there. So if you look at any, here is some spectrum of the XPS. If you look at, you can see different features coming from gold. So this all coming from the core levels, right? So even gold 5D, gold, this one, so L1 or something. So from any this level electron energy you can see in the XPS, or so even other gold 5P. Everyone familiar with PDF, SPDF. So each one has SPDF sub levels, right? So if any electron coming from P level or D, F, everything you can see from the XPS spectrum. That's very easy thing to do. So if you have more material, you will see, like if you use like carbon nanocages, right? You see most of the time you see a feature coming from carbon 1s, because carbon has suborbitals, like you have 2 electrons in 1s, then 2 electrons, so then you have P6 of them. Everybody can be this one, so you can see any electron coming from each orbital. You will see in the X-ray, this XPS spectrum. So it's very easy to see. So if you have oxygen also you will see, like oxygen 1s or even oxygen 1p or something like that. So like we did the fluorination, right? We look at the fluorine 1s peak, actually Alex is this work. So any this information about this binding energy you can get from the XPS. This one. That way, it's very easy to look at. So then, close to this XPS, there's another one called the UPS. UPS is, instead of X-ray, we are using ultraviolet light. So this is the X-ray photo emission. That is XPS. UV photo emission is for the UPS. So this is in the same instrument. So this, I said, this is this one. We had another chamber, like instead of X-ray, we have another one. We have a UV source. So we just shine light on the sample with the UV light and look at what is coming out. Again, use the same detector. You can look at the outcoming energy from the UV light. So in the UV light, situation is different because UV light only excite valence electrons, not the co-electrons. So X-ray has high energy, right? So they excite, eject mostly the co-electrons. The UPS ultraviolet, they eject electrons from the Valence band, not from this one. So now you can see the one, this is the energy of outcoming electron. So this is how it is in the band diagram. So you can see this one has the highest energy, right? Fermi energy. So that energy will be transferred to that has higher energy in the kinetic energy. So this is the lower one, so that you can see like this. You can probe valence band using the UPS. That's the nice thing about UPS. XPS is probing the co-electrons, right? Like K, L, M, any of these. UPS probes the valence band. So you can look at directly, you can look at using this one. This is how XPS is doing, right? You are seeing XPS features here. So this is how UPS features. You can directly probe the valence band. Also, UPS is one of the few techniques you can directly measure the Fermi energy.
What is important for what material is it important?
Oh, the
UV spectroscope.
UV spectroscope is very important if you need to know the work function, Fermi energy. So if somebody wants to measure the work function, so there are 3 techniques you can use. One is UPS, other one is thermionic emission. Remember, when you have a thermionic emission, we have this thermionic current is going something like this, exponential pi over kT. If you measure your thermionic current for different T, you can measure pi.
Yeah.
So I got that, I think somewhere here.
But you use both of these methods?
No, only one of this. Here, this is the thermionic current. This, like T squared exponential. This is the what you call the work function. So you have to measure this thermal current for different temperatures, then you can calculate your Fermi energy. So third one is something called the Kelvin probe. That's also another very useful technique. Please remember those. To measure pi, you can use either UPS or thermal emission, or third one is called the Kelvin probe. Kelvin probe is also very easy. It's simply you have your sample, then you have another some contact. So then when you have, suppose this is your Fermi energy for 1 meter. So this is your material. Then I bring my probe. The probe has different Fermi energy. Right? When you make this contact, what will happen? They will try to equilibrate. Then I think you get the same potential. Okay?
Yeah.
So then you can look at something called this offset voltage. So basically you are measuring the voltage across these two. So by doing that one, you can get the Fermi energy. That's called the Kelvin probe. Maybe next time I'll talk about that. So in this lecture is important for UPS. You can get directly this Fermi energy. You can see. Look at this. Is this clear for everyone? This is the XPS spectrum. So you can see different this L, D, like this feature is 5P, 5D, all these features you can get from XPS. If you look at the UPS picture, you can see this is more like this valence band here, right? You can, then after that you have secondary electron, don't worry about that one. From here, this, if you can measure this position, that will be directly your Fermi energy. That is this position here.
I think.
Yeah, let's take a break now.
One question.
Yeah.
Many students understand about XPS and UPS.
Yeah.
But for which issues, for which purpose, yeah, it's necessary, it's important to measure, for example, Fermi energy.
Yes, yeah. For many, like, especially electronic materials, so even like catalysis, if we have a catalytic material, we need to know where the Fermi energy and the work function are. So, because we need to know the electrochemical potential, so for that, we always is important to know the work function and the Fermi energy.
No, okay. Let's go a little break.
Yeah. Then I think we can easily get to.
Да, давайте передохнем 5 минут, проветрим, может быть.
Here are some of the results from our lab. So we can see yields. This that blowout part. Remember we had yields largely, and this one. So if you look at this in details, you can see this carbon K peak, oxygen K peak, so this silicon L, all these things you can see from that yield spectrum. So then also you can see some interband transition, right? Because incoming electron will lose some energy for the transition. So then you see all those features also coming. Then some surface vibrations, they are happening at low energies, sorry, high energies. No, yeah, that's what we got. This is low energy, you can see what is happening on the surface, not at the bulk. So bulk requires large energy loss, right?
Yeah.
Surface requires only small energy loss. Okay, so I think I'll stop here. Then I think these things probably everybody familiar with the STM, scanning tunneling microscope. So this is a nice technique. You can look at atoms directly. So, I don't know. So this is very simple technique. So what you have is basically your sample, then you have a very sharp tip. So then you have to scan this one over the sample. But when you do this one, important thing is there is this a piezoelectric support here. So always it will try to control current constant. For that you need to have some feedback mechanism. So then what it does is, if you can come to this place is low current, so then it will increase, it will bring it down. Yeah. So if you go to a place like this one, it will move. So that will adjust the height to keep the current constant. So if you do the contours, so these currents are typically picoampere to nanoampere. So by doing that one, you can easily map the samples. So this all happens because of the quantum tunneling, right? So if we have people are familiar with the quantum tunneling effect. Yeah, that's good there. If we have two metals, so this is your, so this is what I was trying to draw here. This is your sample. Then you have it coming here. So then when they are very close to each other, you have this electron wave function. So this wave function will overlap and electron will tunnel from tip to the sample. So from that you can look at the tunneling current. So you can see if this is your incoming wave function. So it is attenuating here, then again going into the your tip. So important thing is, if you look at, this is how tunneling happens, right? You can look at your current is actually given by this K is given by this value here. So this is, everybody does the Schrodinger equation, right? Solving the Schrodinger equation. So this is, you can see this tunneling happens in atomic scale, right? So this is your sample, this is your tip. So tip is very sharp. So
one atom.
Yeah. So but you have these electrons, right? So electron density, they overlap. That's why this electron can easily tunnel from tip to the sample or sample to the tip. So that's why you get the tunneling current. But when the tip is too close, then your current increases. So then the piezoelectric device will try to keep it away to keep the current constant. So that will map the height, right? So that way you can look at the sample in atomic scale. So then similar to STM is something called AFM, atomic force microscope. In this case, similar thing, only thing is we have this sharp tip mounted on a cantilever. So cantilever is something that you support from one end, right? So then you have some way to keep the force between these two constant, not the current. So to keep that one, so this cantilever has to bend the right way to keep the force constant. So to do that one, you have to reflect some light here, laser light here. From that reflectance you can have some detector. So only thing is you need to keep the force constant. That's the important thing in the STM. You have to keep the current constant. In the AFM, you need to keep the force constant. To keep the force constant, then it has to move up and down. So using that same piezoelectric device, so then you can do the mapping. So this is the important thing, this feedback regulator. In both cases, you have feedback controller. This is So feedback controller regulates that. So if you look at, there are different sensors for measure that. This is what most of the AFMs they use. You have a laser light reflector, then you have this quadrant diodes here. So you can use other things too, right? Tunneling or capacitor measurements or piezo resistance or piezoelectricity, anything you can measure to look at the deflection. So but typical AFM they use the beam deflection.
And you use these methods in your research?
No, we only use the AFM, the commercial AFM using this technique.
For nanomaterials?
Yes. The thing is, we are looking at this phosphorine. That's a two-dimensional material. You can only see from AFM, easy to see.
No. And you can see atoms?
No. So AFM you cannot see atoms. You can only see the feature. Important thing is, once you do the AFM, you can measure the thickness. Suppose this is your substrate, right? Suppose this is your sample. So when you move from here, suppose this is, you can, going from here to here, you see some height increase.
Yeah.
From that you can measure how many layers are there. If you have many layers, then this height will be.
And you can decide one layer.
Oh yeah. So typical one layer is about 0.7 nanometers because there is some air between the substrate and the first layer. So also some van der Waals force. So that will keep, usually this thickness is about 0.7 nanometers. So this is how this reflection is measured. So here is a standard AFM tip. So nowadays, actually one of my former students, she and her husband, they started a new company called what they do is they grow, this is the silicon cantilever. Yeah, so this is something like this, right? They grow very sharp silver nanowires. They are very sharp. So they use this one to probe. So they have a company to sell these ones. Even you can use carbon nanotubes. If you can grow carbon nanotubes here, then you can see much finer features. Yeah. So usually this is what when you buy cantilever, that's how they look like.
What's the price?
This we recently bought. This, you can get about 10 these tips for about less than $100. They are only tips, real small, right? This small box they come about. Usually we order like 20 at a time.
And what about the using time?
Oh, so they, if you use, I'll talk about, there's something called the contact mode and the non-contact mode. If you use the contact mode, maybe after 4 or 5 samples you have to replace the tip. If you non-contact mode, you can use for like 10-20 times.
And what is typical area?
Typically, we in the one we have, we can do about 20 micrometers. Or 30 maybe. 30 micrometers per 30 micrometers.
It's big if you are working with the nano.
Yeah, we don't need that much, yes. But typically, if you want to get this height, we like to get the height from both ends. This one and this one, then it's more accurate, right? Not from one end. That's how we do it.
If you use nanotubes, resolution is higher.
Oh yes. So if you use this one, your resolution will be.
To compare with ours.
Yeah, I think if you want to look at things like DNA molecules and things like that, so they like to use this technique. They use in the much finer ones. But I don't see any need for my research.
What about the resolution of translational stage?
Oh, that you can control in the very maybe sub-micrometer scale easily. Yeah.
Or if we have a piezo?
Yes, yeah, they all are piezo. Yes, yeah, yeah.
It's
So they all piezo. So like I said, when you use this you can use something called the contact mode or non-contact mode. Contact mode is, we know, when you are far away from your tip, right? So then your forces are more attractive. So when you get too close, then this Pauli exclusion principle, so that makes it repulsive, right? So then, yeah, so that's why typically, yeah, so they happens in the contact mode. You can see this, in this range, this becomes positive, this becomes negative here. So this is the force actually. Force is negative of your negative E over dx, right? So depending on what mode, so this is where you use the non-contact mode. So that is your force is negative. Yeah, in the contact mode, usually we use in this way, in the positive mode. So also we have to be careful with the frequency. When you buy the AFM tip, you need to know what oscillating frequency. These are typical like kilohertz frequencies, and also you need to know what is the spring constant. Typically we use like 40 newtons per meter or maybe 5 newtons per meter, depending on contact versus non-contact. You need to find the right. Otherwise you can easily break it, right? If you use the contact mode, it should be too stiff. Then it will damage the sample, and also it can easily break.
Слишком жесткий может зацепиться и сломаться. Why do we need to have a
Oh, that's how you modulate to get the your.
It's for a better
Signal. Yes, yeah. Okay, so I think that's more details. So here you can see in STM, you can see all these atoms very nicely, right? So I don't know whether they have seen IBM people. They even wrote IBM with the STM. They can, these letters they could move.
Yeah, you also can move.
Atoms. Yes, yeah, you can easily all these atoms. But with the AFM, you can only get features like this. But still, this is DNA molecule. So another important thing is for STM, you need to have a conducting sample because this is electron tunneling, right? You need to have enough electron. But the AFM you can do on any insulating material. That's one important difference.
Oh yeah.
STM you cannot do on insulating samples because you have to have enough electron tunneling, right? Okay, so then I will quickly go through some optical. So far we were talking about electrons, right? Now if you want to use the optical, so everybody familiar with the how electric and magnetic field and their frequencies, Maxwell equations, those are the fundamental things. So then the frequency, energy ranges, all these things. So these are some of the techniques people use. So if you go from X-ray, all these things, that's why you need to have angstrom nanometer scale. But if you use other techniques, these are mostly, this is the optical one, right? So up to here. So then you can have other ranges like microwave. These are like gigahertz frequency. So different. So that's a different scale. I'm only going to talk about maybe this part here. UV absorption and infrared and Raman spectroscopy. you can see there are so many different spectroscopies, right, for different length scales and frequency scales. So another important thing is to, if you look at this spectra, you will see different scales, right? So if you look at the energy scale, sometimes you will see it's in hertz.
Yeah.
Sometimes you see it's in length scale, and sometimes you see it's in centimeter inverse, right? Because in Raman spectroscopy, always the x-axis is written as centimeter inverse, because we know that's right energy scale, right? Because E is hc over lambda. So if you take this one, this is in inverse length scale. So don't get confused. So you can have any kind of this energy. This is your intensity. Doesn't matter. This is energy unit. Can be centimeter inverse. Can be this. Also, this is H frequency, right? It can be hertz. So it can be. Sometimes people even draw this way lambda. So there are different scales. Also, you can convert them into temperature. So we know. Everybody should know this one, right? 1 electron volt is 1.23 over your lambda. Also, all these things are very important things to remember. So then, probably you have UV spectrometer. I think that's very common, right?
No, it's part of the parenting, but
so this is the most fundamental spectrometer, right? It's basically you have your sample, then you have your light coming here, so then you have your detector here, then you get the transmitted light. Or if your sample is not transparent, then you have to use the reflective one, right?
Yes.
So rather than here we know always your incoming one is you have transmitted one plus reflected one plus any absorption, right?
Mm-hmm.
That's what we need is this one basically. So in this case, if you measure T, you can get information about your absorption, right? But if your sample is a solid material like this, light cannot go through, right? Then what do? We use something called the diffuse scattering, reflective measurement. So in that case, you have this one. You look at what is reflected from here. Your detector is here now. From that, you can get you have no transmitter term here. So if you look at R, you can get the information about what you measure is typically absorption. So here, if you look at simple metals, your absorption can be due to any transitions from. So here I'm looking at typical molecular bonding and anti-bonding states. So we call the sigma, this sigma bond by this is a typical organic molecule, right? So if you have any transition like this, you can see those features in the absorption, right? So this coming from this transition and this coming from this transition. Any absorption you can look at very easily from the UV visible. UV visible means you are basically going from about 200 nanometer to maybe close to 2000 nanometer. Right? But you have to be careful with the water absorption. So then, not only that, you can look at other like plasmonic absorption. If you use something like metal, like gold nanoparticles or something like, if your gold nanoparticle has certain size, you will see some absorption coming from the plasmon absorption. All these things you can easily measure from UV spectrometer. But what is more important is, this is very important to if you have a semiconductor. So you can easily tell from this UV absorption whether it's a direct band gap or indirect band gap. You know, in semiconductors we have conduction band and the valence band, right? So if they are at the same K, suppose this is a gamma point, so this is a K, the momentum space. So if they are, this is a direct band gap, right? So if it is like this, they are different position, then they are, we call it indirect band gap. So that means you need to have, if here directly if you have some light coming here, electron can go from here to here, right? So, but in this case, if you have h nu, you need to have momentum also conserved. So that means you need to have another, we call phonon. Right? So you need to have this additional, you need to have phonon contribution. So you can directly tell from UV spectrometer whether this is a direct or indirect band gap. So
how can we see?
Yeah, that's actually if you look at your alpha absorption as a function of h nu, for direct band gap, they find this alpha is proportional to this h nu minus, suppose this is your band gap. This is half the square root of this one. So that means if you plot alpha square is h nu minus Eg. So suppose this is alpha square, you will see a straight line. So this is directly, this value will be Eg, right? So, but if it is indirect band gap, this alpha is h nu minus Eg, then also you have this phonon term. So this is typically square. So that means you need to take alpha half, this becomes h nu minus Eg minus epsilon. If you plot, in this case h squared, in this case you have to have square root of alpha h nu. This will give you some straight line, but that this one is Eg minus h cross omega. So this value is h cross, sorry, you have Eg minus h cross omega. This is your phonon term. But this is very small, so then you can take this one as your band gap. So here I have drawn that one. So this is what for direct band gap, this is square root of 1. For indirect band gap, this is square. This is very important. So this is how people immediately tell whether this is a direct band gap or indirect band gap. Very quick way to look at that. So next we'll talk about Raman spectroscopy. Everybody familiar with Raman spectroscopy? Basically having come in laser, then you have some vibrations. So again, there's some absorption. Then your scattered light will have changed frequency, right? So from that you can get the. So here is the typically vibrations. So you can see there are two kind of Raman. It's called the stokes. That means you. So if you have same. You excite, then if the same thing coming out, we call it as a fading scattering, right? There's no change in your frequency. But in the Raman case, stokes means you have energy less than that one, because this is going to be, this is how it's initially excited, then due to phonon creation, it will lose some energy. Now you are only emitting less energy. But in this case, anti-stoke is you are, we call the annihilation of phonon. That means you have higher energy, then you get higher energy. That means if you get the difference, that's the negative part, right? This is Stokes part, this is the anti-stoke part.
Да, смотрите, получается у нас излучение взаимодействует с веществом. Может быть упругое рассеяние, это релеевское, может быть еще стоксовское, когда энергия излученного фотона меньше, и антистоксовская, когда она больше. Вот, и это в брауновском спектрометре фиксируется.
So basically people are only looking at the stroke because anti-stroke is very weak. If you look at typically Raman spectroscopy, what you are measuring is this change in your wavelength, right? 1 over lambda initial, 1 over lambda final. So this change in your 1 over delta lambda. So typically you are seeing some Raman features like that, strokes, but anti-stroke one, anti-stroke one comes. This one that is very weak. So that's very hard to, this one only people look at the strokes one. But if you measure anti-stroke, you can get the temperature and things like that. So, I will go through that one. So this explains how the phonons are created. So initial one, this is the scattered one. So plus means you create a phonon, minus means we call it annihilate the phonon. Right? So that's depending on that you can get different in your lambda. So I don't know whether you're familiar with this one. This is the phonon density of state. So dispersion curve. This is the phonon energy with the phonon wave vector. We call this is acoustic mode. So this is the optical mode. So with Raman we can look at what is happening at this gamma point here. I don't know whether so this is for two atom. Sorry, two atom. This. If you have two atoms in this string configuration, right? If you solve this normal mode, you can generate this. So this is what you are looking at, optical branch from the Raman. We are only looking at this zero Q vector Raman features. So here you can see some of some perovskite material. So you can see a lot of Raman modes. So this means transverse optical. This means longitudinal optical. So every familiar the transverse versus longitudinal. Transverse means it's always if you have two atoms, both atoms always goes. One goes up, other one goes down. That's the transverse. Longitudinal means both atoms move in the same direction. So that's what TO is the transverse. All optical. We are not looking at this is the optical mode. This is the acoustic mode. There's a spectroscope called Brilliant scattering. So that is to probe the acoustic modes, but optical is what we use for the Raman. So Raman optical mode also can have transverse or longitudinal. Transverse means if you have two atoms, so either they both go up from here or they both go down like it's like that, right? So longitudinal means if one goes up, other one also goes the same direction. So here actually I didn't go it right. So here that's what this TO, LO, all these things. So typically there's a rule. If we have S number of atoms in the unit cell, this perovskite has 5 atoms per unit cell. So then typically you have 3 S time modes. So this is 15, right? There are always 3 acoustic modes. Why is that? There's one always in the direction of the wave, other one in X and Y direction. So that means there are always 3 acoustic modes. So rest should be all optical modes. So if you have 5 atoms per unit cell, always acoustic modes, they have always 3. This 3 means 1 longitudinal and 2 transverse. Because if it is wave is this way, so then atoms can move that way, or waves move this way, then atoms can go in the x direction or y direction. There are always 3. Then you have 5 times 3, 15 total. Then 15 minus 3, 12, you have optical modes. So here you can see most of those modes that come here. Should have about 15. This is standard way to remember how many modes you can expect. Okay, so last thing is IR spectroscopy, infrared. So these are mostly looking at features happening at this infrared ranges, like going to your micrometer scale, right? So they are mostly looking at vibrations of electronic transitions, vibrational and rotational, all these things, right? So you can see some of the IR vibrations. You can have this symmetrical and symmetrical, we call the scissor mode, rocking mode. So they all are infrared active spectrum. So typical spectrometer, you have again infrared source, then sample, then you have a reference source, then we are looking at the difference between the two. But nowadays nobody is using this one, everybody is using something called FTIR, Fourier transform. So they just measure directly at the time, then they Fourier transform back to your frequency. That's nobody is using this one anymore. Everywhere we go, you find something called FTIR, Fourier transform infrared spectroscopy. That's very easy. It's very quick. Here you have to do for different lambda and look at the absorption, right? Over there, you just look at the given time, you just measure the spectra and just Fourier transform into lambda. So this is very easy, like we know if you take organic materials, we know all these like energy where it should be. If you take this double bonds and triple bond, so this range, double bond is in this range, also other like carbon, nitrogen. These are standard numbers. You can directly tell what kind of bonding is there. But that's very rich. The IR spectrum is sometimes very hard to analyze. You get too many things. So here, if you look at formaldehyde, you can see these are coming from CH2, symmetry, CO band, CH2, all this you can easily figure out. But sometimes it can be very difficult. But this is also very standard technique. Okay, this is getting late. I'll stop here. I was thinking about doing a few more things. Yeah, there's some comparison between Raman and FTIR. So last thing, luminescence. Last thing, photoluminescence. That's also very important technique. People are familiar with the photoluminescence. Photoluminescence is in a semiconductor. If you can excite electron from here to here, so then you have hole here, right? So then you have electron here. So then they like to come back together, right?
Combine,
Yeah. So we call the recombination. When they come together, they have to emit, because when it comes here, they don't stay here. They like to thermalize to this place, right? So now this also thermalized to this one. So now it will fall down, but emitting energy. So this energy is smaller than this energy, right? This is input energy, this is output energy. So this is smaller than this one. So depending on this band gap, you see different colors. So you can easily measure your band gap using the luminescence. So, but sometimes if you have some defect state here, so then electron can get trapped here. So then it will come from here to here, it will emit another emission field. So that means you can have, we call this the band-to-band transition, or you can have something, if this is energy scale, something happening at the lower band, that is this transition. Right? So those information you can get from photoluminescence. So this is what I was trying to say. This is you, with this one you excite here, they will come down here in this emitted photon. So here are some of the details you can do at low temperature. So here are some of the luminescence peaks at different temperature, because there's a temperature term here. So always photoluminescence are very weak at room temperature. So you have to do at lower temperature because of this population term, right? So it's actually here. It's a Boltzmann energy term. So if you want to get good spectrum, you have to cool it down. This is how it looks at room temperature. And when you go to 6 Kelvin, you see very strong things. So like in our lab we have something called the Lincoln stage. You can cool it down. Right now we don't have helium temperature, we do only 77 Kelvin for liquid nitrogen. Okay, I'll stop here, that's too much.
Thank you. Guys, what about questions?
Yeah, if you have any question. This, at least you get some idea we have to look for.
We can share the slides.
Oh yeah, I'll give all the slides to students.
Okay, thank you.
So,